All right, our next speaker and last one of this session before the break is Dr. Oral Lazar.
Sorry about this. Okay, so just to give you a sense of my background, I spent some 15 years in information theory, communication theory, control theory, but mostly actually in computer networks, what is called today the internet. I was away from Columbia for 3 years. I had a startup, and when I came back, I decided to switch fields, and I got into essentially computational neuroscience by way of information theory and signal processing. And then as soon as NVIDIA opened up their chips, which was something around 2007, 2008, we switched into parallel computing on NVIDIA chips. And then we also learned how to do patch clamping on fruit flies. That was quite an experience because, all my background before was in sort of hardcore hardware operating systems, game theory, that sort of stuff. And so I switched. And the reason for switching was in part because I felt that Moore's Law is going to start creating huge problems for IT. And there was a need, at least in the geeks world, which I was part of, to look at machines which are actually intelligent in some ways. So first what I'm going to do is I'll talk about some elements of foundational elements, and I'll start with neural encoding in the time domain. And I'm giving here an example of the difficulties involved in neuroscience, and from a information processing standpoint, the main difficulty comes from the fact that everything is nonlinear. If you come across a problem in neuroscience which is linear, just forget about it, okay? It's not interesting. Either the model is too simplistic or one misses the point. And so I'm giving here an example of a case where what we have is what is called complex cells. They appear in V1 in the visual system. And what you see here in terms of modeling, this is the spike generator, which is typically associated, let's say, with Hodgkin-Huxley neurons or integrated fire neurons, what have you. It doesn't really matter. So it can be biophysical models, or it can be sort of idealized, simpler models like the threshold and fire neuron or integrated fire neuron. And behind it, what you have here is a model of the dendritic tree. And this here is modeled through convolutional filters here. You see G here and G here, there are two convolutional filters, but the difficulty appears because the output is squared. So as soon as you get squaring, essentially you have a nonlinearity here, so you have a nonlinearity coming from processing the visual field, and the nonlinearity is of the type, of energy type, and you add these things up into the dendritic tree, and suddenly you have a huge problem because signal processing, as soon as you go to nonlinear operations, it's poorly understood. And then, of course, this is highly nonlinear. So essentially, the signal generator, the axon hillock of the neuron, is nonlinear, and so is the dendritic tree. And now the question is, what can one say by observing the spike trains here? And this could be maybe 100,000 neurons running in parallel. Each neuron, in the case of the Hodgkin-Huxley neuron model, has 4 differential equations, which nobody understands because they're highly nonlinear. And so you have 100,000 outputs, and you're encoding maybe a movie in real time. You ask the question, what can you say about the input which has been encoded in the spike trains? So note, the important thing from our standpoint here is that we have an analog waveform coming at the input, and the output is a time domain sequence. A time domain does not appear in information theory. Time domain discussions do not appear in models of computer science, so that if you look at the Turing machine model, there's no concept of time, there's no reasoning about time, there's no program verification about time. So what that means is every time you fly, just think about it, that it's never clear whether the plane is going to arrive, because there's no formal verification that it's going to arrive. Now, what happens here is the question is, if I look at the output, can I say something about the input? And interestingly enough, actually, we can say something very strong, which is a result similar to what happens in Shannon sampling in classical signal processing. So it's a topic which does not appear in the information theory book, but appears in books prior to that. And here I'm giving an example of this. So you see on the top, on the left, there's a bee in a natural environment. And this is the original, this is the recovered. And there's no difference between the two. Essentially, you can look at the Fourier transform, you can make difference in all this, but essentially, one is perfect recovery possible. So this is the case now with all these videos. I'm just showing different examples so you get a sense of this. Now, what is the importance of this? Sorry. What is the importance of this? That mathematically, actually, one can write theorems and proofs, and one can demonstrate that that's the case. And essentially, the result says that under Nyquist-type ray conditions, the representation of sensory information in the spike domain provides a foundational element for information communications and coding theory. So in order to start talking about information theory in this context, in order to talk about communication theory, coding theory, one needs actually a theorem which tells you that let's say the visual space can be represented in the time domain. And because everything is nonlinear, this originally was a big headache to demonstrate, but now we have results of this sort. So this is very powerful, because suddenly these fields actually have a foundation on which one can build. Exactly as is the case today in information theory, et cetera, where there's Shannon sampling, and we know how to build things on top of it. Now remember, Shannon sampling means amplitude sampling. There's no concept of time. There's a concept of a counter. Okay, there's an amplitude which is being basically sampled, but there's no information representation in the time domain. Here, the information is represented in the time domain because these are spikes. Okay, so now, what next I'm going to show is that one can talk about, in a rigorous fashion, about space-time predictive coding in near information processing. And I'm going to give an example again without going into details. What you see here on the left is sort of a model of the retina. These are basically photoreceptors. And specifically, we are looking at a case of the fruit fly, because this is where my interests are. But you can think about this the same way with the retina. And what happens is, behind the photoreceptors, there is a set of so-called amacrine cells, which what they do is they get input from the photoreceptors and they provide feedback. So as soon as you get feedback, of course, timing is super important. And the question is, what does it do? And how can you interpret it? And is this actually a tractable problem? So what we did is we modeled this. I'm not going to go into the details of this, but if you are sort of interested or you have background in this, what happens is at the input we have there U1 to UN. These are pixels essentially, or discrete elements in space. And then what happens is the system is processing these pixels through Volterra processors, which essentially can be interpreted as being first and second order filters. As soon as you bring in second order filters, essentially that means is a quadratic nonlinearity, so the problem becomes highly nonlinear. But what is more interesting here is the fact that we have a divisive normalization processor. There's a division involved. In IT, divisions are avoided because they're very computationally intensive. But it looks that that's not the case, at least in the fruit fly. And actually, there are examples for other neural systems where this divisive normalization has been demonstrated to be very effective. And so what you see here is this. You have an input here, which is in the time domain, and then there is a time domain feedback involved through a division. So the way you want to understand this is that you have a term here, which is the nominator, and then there are some terms here, which are the denominators. So there is time domain feedback, but there is also spatial feedback. So this looks like a nightmare, basically, computationally, also theoretically, I should say. But as it turns out, this is actually highly tractable if one looks at it, quote unquote, from the right angle. Now, intuitively, I'm using the word here, predictive coding, and essentially what this divisive normalization is doing is predictive coding. And the way to understand this is like this. If you have a division, if you take the log of the division, you have a subtraction between the log of numerator and the log of the denominator. And subtractions are something which we are used from predictive theory, let's say Kalman filtering. And so if you like, it's a nonlinear predictor, which makes it actually quite interesting. And this can be then looked upon also in terms of how this is exactly implemented on the molecular level. Now, what's the impact on this? I'm showing here a processing with a circuit like this. So this is modeling the retina with feedback, and you can see here is the input. You see nothing here because the luminance is very low, so the contrast is very poor. And then here you have higher luminance, and it is even higher. And then suddenly you see what happens is the photoreceptor does some processing on it, but the photoreceptors plus the feedback, it does processing that you can see exactly what's going on. And this is actually quite pleasing and surprising, if you like. Now, I see that I have to finish here soon. So connection to the previous talks. So I think that a class of interesting problems is associated with the fruit fly, and in part is because the brain of the fruit fly is numerically very small, maybe 150,000 neurons, but also because, as you will see probably in the press this week, the fruit fly has been sliced, imaged, and the connectome reconstructed, at least for a large part of it. And that essentially means that this is going to be a brain which provides us a lot of information. And now we look specifically at olfaction, and olfaction consists of an odorant space. Then this is odorant information representation. This is now a predictive coding in the antennal lobe. And this is here associative learning in the mushroom body, and this is innate learning. So understanding this circuit, and this is what we're working on, is very timely, and it's actually going to give us information which is well beyond what is being talked about in learning theory today, we believe. I'm just giving an example to connect to the previous talks here, how we look at the information representation in the molecular domain. There's probably not much time to continue this. I have a minute. Okay, wonderful. So you see, what happens is this. I'm showing here the transduction in the fruit fly olfactory sensory neurons, and it starts with basically some filtering in sensilla. These are hair cells, which have essentially some quote-unquote holes through which the odorant gets in, is bound to the receptors. This is related to the first talk Tom was talking about. I think that we need to discuss this a little bit because we are seeing that this is sort of the information is represented right there at the photoreceptor level, and then there are some feedbacks due to calcium regeneration, et cetera, which I cannot go into the detail, but you can see that suddenly now I'm not showing filters, I'm not showing Volterra operators, I'm not showing spikers. What I'm showing here is that there's a transduction process, all chemical. Now, this is interesting because now if I look at another system, and Tom mentioned channel-rhodopsin, channel-rhodopsin and these receptors work in the same way. I should say not channel-rhodopsin, I should say rhodopsin. And these receptors actually work in the same way. There are some details huge details about it. It's very interesting. But what I'd like to bring in here now, if we want to understand how the brain works and In the end, that's what we want to do, at least from my standpoint. There's a need to start talking about neuromodulation, and neuromodulation is all chemical. And what's happening is basically, there are bunches of synapses in groups, and they are essentially controlled through neuromodulation. And this is sort of very interesting. If you're coming at it from an IT standpoint, it's like you have a box where there's an input and has an output. It's running, and suddenly you change the way the logic of the box works through another interface, like say through a wireless interface. And suddenly the input-output mapping changes. And suddenly you are dealing then with a class of problems which is actually probably goes to the heart of the story in brain computation. So from that standpoint, understanding the molecular architecture of the brain is really central to all this. So as I mentioned before, representation of information in the time domain, we have a very good understanding of it, we believe. But we also think that there's a need to, whatever one does, one has to bring in time explicitly in the models. And information theory has no time concept. So, you might be very disturbed by this, but it's very clear it's not there. Turing machines don't have the time concept. And so a program of research has to bring this in. Now, what do we want to do is essentially bring in models of molecular computation of brain circuits. So it's not enough to look, as there was a question here about how do you scale this up. You see, we see the scaling. The question now is whether we can provide meaning for this. Also, without just going into all these details, I'd like just to emphasize the following thing. Information theory is very powerful in the context of information transmission. Everything, however, looks the same. The information we have to encode, however, is not the same. And there is no model for this. It does not appear anywhere. Here, you see the first time where this appears is that the odorous stimulus actually has an identity. The identity is most likely recognized on the molecular level, and that information has to be somehow transmitted, has to be formalized, has to be presented. And information theory alone doesn't do this, because a bit is a bit, and there's no distinction between those. Let me stop here.
Thank you very much. Thank you very much for that, Oral. And let's just go ahead and give another round of applause to all the speakers in this session, and then we're going to adjourn to the poster session.